So let us resume our discussion in the time-independent perturbation theory regime, where in the previous class we learned about if there is a perturbation Hamiltonian which is correcting the correct description of the Hamiltonian which we are discussing about, then both the eigenvalues as well as the eigenfunctions do change as a function of the parameter which comes with the Hamiltonian. So with the lambda parameter which appears as a correction, the wave function as well as the eigenvalue of the energy gets corrected as a function of lambda, and we expanded these corrections in a power series of lambda. So I would have uncorrected wave function plus first order correction coming with parameter lambda, second order correction to that coming with parameter lambda square, and so on. And similarly, in the energy as well, the same game will happen, that it would have unperturbed energy and then first order correction coming with lambda, then the second order correction to energy with order lambda square, and so on. Our job was to find out what are these correction functions in the eigenfunction and in the energy eigenvalue as well. So we ended up getting these results, that if I have a perturbation Hamiltonian H1, that brings out this as the first order correction in the eigenvalue En1. This is the first order correction, which is just the expectation of the perturbation Hamiltonian between the states of nth eigenenergy level of unperturbed Hamiltonian. Similarly, we found out that the first order correction to the wave function psi n1 is an expansion over the basis of the unperturbed Hamiltonian. Just one term is missing, which is the eigenfunction itself over which the correction is being found out. And these corrections psi n1 are totally characterized by the coefficient CNMs which are coming here. So if I know what are the CNMs, I know what is the correction, first order correction to the wave function. And we found out that these CNMs are also to be obtained from the matrix element of the Hamiltonian. So we obtained that these CNMs or CNLs I have written over here are nothing but the matrix element of the perturbation Hamiltonian H1 squeezed between psi n of the unperturbed state from the right and psi l, the unperturbed lth energy eigenstate from the left. So on the numerator, I have a nth matrix element of the perturbation Hamiltonian H1, and that gets divided by the energy difference between the unperturbed eigenfunctions, eigenstates En0 and El0. So we computed those things for harmonic oscillator with a Hamiltonian which is relativistic correction to the kinetic energy, and we found out what is the first order correction to the energy eigenvalue En1, and we also found out what are the corrections to the first order correction to the energy eigenstate CNLs. In particular, I wanted to know how much the ground states get changed. So we learned that the ground state becomes the unperturbed ground state plus first order correction is C02 coming with the second excited state, the second order correction, the second correction which is still at order lambda. All these things are at order lambda itself. They are coming with coefficient C02, C04 and so on. C01 for example is 0 as we computed. C03 is also 0, and you are left out. You were given a task of finding out what is C02. The computation is simple. Alright. So now let us cement this notion with one more computation, one more example where we will be discussing an atom talking to externally applied field. I am taking this example because throughout the course, when we develop it further, one idea of the course is to discuss matter-field interaction. So as we evolve in the course, we will see more and more examples of this, where we not only try to learn about what happens to atom, but we also invoke quantum features to the externally applied field as well. So it is a good idea to start with the classical field as an externally applied agent. So what we talk about is a hydrogen atom whose Hamiltonian is kinetic energy minus the Coulomb potential, which is the unperturbed Hamiltonian H naught, as we know. And then there is a correction term which is coming from application of an externally applied electric field. The electron, for which we are trying to write down this Hamiltonian, will see the electric field present and would therefore feel an electric potential, which is the amount of electric field which is constant in time. I am assuming this, that it is constant in time, because we are doing time independent perturbation theory. For that constant electric field, the electric potential is E times Z. If I have applied the electric field in the Z direction, this is the potential I would be getting. Potential energy of the electron put in the electric potential phi. Now you can see that the electric field is the minus of the gradient of the potential. Therefore, with the potential being minus E times E being the electric field magnitude times Z, then it becomes its gradient just becomes constant electric field in the Z direction. Now in spherical polar coordinate system, the coordinate Z can be written as r cos theta, as you are familiar with. This is the Z axis, this is the x axis, and this is the y axis, and the angle which it makes with the Z axis is the angle theta. Now perturbation Hamiltonian is known to us, which is E r cos theta. The position operator r is the parameter which is coming in as an operator. So we will work in the position representation of the system. In any case, the first order correction to, let us say, the ground state of hydrogen atom is n is equal to 1. Remember, unperturbed energy eigenstates of hydrogen atom was minus 13.6 eV upon n square. So therefore n is equal to 1 is the ground state. If I want to know what is the first order correction to the ground state, so I will compute E11, n being 1, and this 1 upstairs is the first order correction. That would be the perturbation Hamiltonian squeezed between the ground states. So this exercise we have to do. So I have H1, which is known to me, which is nothing but E times electric field and times r cos theta, which is Z. And this has to be squeezed between the ground state. That means in position representation, I have to integrate the perturbation Hamiltonian with psi 1 star r from the left and psi 1 r from the right, the ground state wave function. And we know in hydrogen atom, the ground state wave function is this, exponential minus r upon a naught with a constant factor which is coming outside, where a naught is the Bohr radius, as we understand. So we can do this computation. We can evaluate this integral by just putting psi 1 here and psi 1 star here, and you will get an integration of this kind. You will see that the exponential will get doubled, e to the power minus 2r upon a naught, and pi a naught cube will come from the square of these quantities, because psi 1 star and psi 1 are coming about. Now the measure, the d3r, can be written as d phi integral, sine theta d theta integral, which can be compactly written as d cos theta integral. In sine theta d theta case, the angle would run from 0 to pi, but if I use d cos theta, the cos theta will run from minus 1 to 1. Then in this case, the radial parts measure will be dr times r square. So this is just d3r written in their respective limits. And this overall is the psi 1 mod square, which is coming from psi 1 here and psi 1 star here. and this object r cos theta times minus of EE is just the Hamiltonian of perturbation. So ultimately I have to do this integration. Phi integral is simple to do because the phi integration is simple to do because it runs, there is no phi dependence in the expression. Okay, so let us move to another example to see these things in action. So we will consider a hydrogen atom. Electron in that is interacting with an electric field which is applied externally. So we will be dealing with these examples more and more, because in this event of this course and during discussions of course, one idea is to develop the understanding of matter field interaction. So therefore we will see these kind of examples very frequently. So it is a good idea to build things, start from the very beginnings, starting with a classical electric field which is time independent. So a constant electric field is applied in a direction z such that the electron in the hydrogen atom, which was already living under unperturbed Hamiltonian, which was kinetic term plus Coulomb potential, so that was the unperturbed Hamiltonian H0. And now due to application of the externally applied electric field, there is another term which is electric charge times the potential of the electric field, E phi. Phi happens to be minus E times Z, where phi is minus E times Z. That means the electric field is minus of the gradient of phi, which is equal to E along the Z direction. So this is how the Hamiltonian of such a system is written. We know that unperturbed system, which is the ordinary hydrogen atom, the electrons live in energy eigenstates with eigenvalues given by this expression over here. En0 unperturbed eigenstates are minus 13.6 eV upon n square, where n denotes which eigenstate we are talking about. Ground state is n is equal to 1. First excited state is n is equal to 2. Second excited state is n is equal to 3, and so on. So I hope these things are familiar to you through your discussions or your exposure to quantum mechanics. Now we want to know, under the action of the external electric field, this Hamiltonian, what happens to the ground state energy? Does it remain minus 13.6 eV upon n square, where n is equal to 1 or 2 or 3 depending upon which state we are talking about? So we want to know what happens to any general eigenstates energy, whether it shifts, and if it shifts, by how much amount. For a particular case, I am interested in knowing what is the first order correction in the energy eigenvalue of the ground state. That means I want to know how much change at the leading order lambda is brought about by the perturbation of this Hamiltonian. So H1 is E times phi. Okay. So in order to compute the first order correction, what I have to do, I have to take the Hamiltonian, which is E times phi, and since phi is minus E times Z, the Hamiltonian therefore becomes minus E times capital E, which is electric field, times Z, and squeeze it between the ground states, n is equal to 1. So that would be the first order correction to the energy eigenvalue of the ground state. In order to do so, I have to compute this object. One easier way of computing this is going to the position representation. For harmonic oscillator, it was more convenient to work with bracket notations, and in this case, it is more convenient to work in the position representation. So I will just evaluate this thing in position basis. For that, I need to know how does the wave function, ground state wave function psi1 look like in the position representation. We all know the answer. It looks like an exponentially decaying function, e to the power minus r upon a0, with a normalization dictated by root pi and a0 to the power 3 by 2, where this a0 is the Bohr radius. So this is about the wave function. Its conjugate, the bra psi1, would be just complex conjugation of this. The Hamiltonian itself, this would be E times Z. Z in the radial coordinate or spherically polar coordinates, Z would be written as r cos theta. So given Z, given r, vector r, its projection along the z-axis is r cos theta. So now we are ready. We have the position representation of the wave function. We have the position representation of the Hamiltonian of perturbation. And then we can compute the first order correction to the ground state energy. So En1 ground state first order correction is this integral psi 1 star, which is together making psi 1 mod square, and the Hamiltonian. So let us write these things nicely. The d3r integral, which is appearing over here, can be broken into three pieces: d phi integrals from 0 to 2 pi, d theta integral with a sine theta coefficient, which can collectively be written as a d cos theta running from -1 to 1, and dr integration with a measure r square running from 0 to infinity. So this whole thing, the three limits integral is just a total volume integral in spherical polar coordinates. After that, I have a Hamiltonian E times capital E times r cos theta, where r cos theta was z, and psi mod square. So psi mod square will be exponential with twice the argument divided by square of the denominator of the wave function. So all these things are fine. D phi integral is easy to do because nothing depends on phi. I will just get a 2 pi out of this integral. Only contributions will come from cos theta integral because there is a cos theta over here, and dr integral because functions depends on r. However, before going to r integral, if we just do the d cos theta integral, you can call cos theta as y. So it will search for cos theta everywhere. So only time cos theta appears is here in the Hamiltonian. So ultimately it becomes -1 to 1 dy of a y. The cos theta integral is just coming with one cos theta appearance. So you know the answer, -1 to 1 dy of y, an odd function under symmetric limit, is 0. So therefore the theta integral exactly vanishes, and therefore whatever be the result of the r integral, if it is finite, finite times a 0 will be 0. So therefore ground state energy does not change under perturbation at the leading order. That means at the order of lambda it does not change. Maybe at order lambda square it changes. En1 happens to be 0. That does not mean En2 is also 0, En3 is also 0. And this is true for n is equal to 1 only. If I went on to compute what is the answer for n is equal to 2, I might not get a 0. So therefore one has to be very careful. This tells me only that first order correction for the ground state is 0. This is not a general statement. It is not a statement about any order. It is not a statement about any eigenfunction. It is only true for first order for n is equal to 1. So we have seen the ground state does not change at the first order in eigenvalue. The eigenvalue does not change. Does it mean eigenfunction also does not change? Let us check that and let us go downwards. In order to know that, I need to compute these coefficients C1L. If C1L happens to be 0 for all else, then I can say that there are no changes in the ground state wave function as well. Remember, we had learned that we have to compute CNLs, because these CNLs decided for me what is the first order correction. Psi n1 was supposed to be summation over L for all the states which are not n of CNL, and then psi L of the unperturbed basis. So we need to know what is the CNLs. If all the CNLs are 0, then I can say that the first order correction to the wave function is also 0. So we have just seen that En1 for n is equal to 1 is 0. I want to know whether C1L is 0 or not. So let us do the computation. As we have seen, C1L will be obtainable from taking the Hamiltonian, the perturbation Hamiltonian, which was minus EER r cos theta squeezed between psi n, which is n is equal to 1 from the right, and psi l, l from the left. So this integration we have to do. So C1L has this computation. L can be any other state, not n is equal to 1. In hydrogen atom, I know what are the states for me. There is a ground state which in the NLM basis is given by 100. We are trying to get the correction into this. And then the first excited state 200. Actually, there are 3 more of them at n is equal to 2. 210 is there, 211 is there, and 21 minus 1 is there. This is for n is equal to 2. This was for n is equal to 1. So I want to know C1L. L is supposed to be all other states, but not just the ground state. It cannot be the same value for which you are trying to find out the correction. We are trying to find out the correction for ground state, n is equal to 1. So L has to take all other states. This L right now is just indication of summation over all the states. We could have called it M as well, let us say M, or some other symbol, not called M or L, because we are using L and M here as well. So let us call it some alpha, and then it has to be alpha. Now this alpha is the label of all other states. All other states are labeled by 3 numbers, N, L, and M. Alpha is a collective name of N, L, and M. So therefore, I cannot take alpha as 100 because that is the state, ground state, which we are trying to find the perturbations for. So the next value alpha can take is 200. So C1 200. So that we can compute like here. Here L. So now we are calling it alpha. Alpha has to be supplied as 200. So I will supply 200 here. This is the Hamiltonian r cos theta times minus E upon E. So there is a minus cancellation which I should do. And then the psi alpha, which is psi 200, the ground state on the right and the Hamiltonian in the middle. You can again write down the position representation of psi 100, which we had already written in the previous slides, and you can look up any textbook on quantum mechanics of hydrogen atom. Then you will find out that psi 200, this state, as a position representation of this kind, exponential with 1 minus r upon 2a naught extra factor and some normalization. Okay, again the same thing. You see, this psi 200 does not depend on theta. It is free of theta. It only depends on r. Psi 100 is again free of theta. So like before, d phi integral we go from 0 to 2 pi will give me 2 pi, but d cos theta integral, previously it was vanishing because of the cos theta appearing in the Hamiltonian. Only one cos theta was appearing. That made it odd function. This time again, since the wave function psi 200 also does not depend on theta, so the previous argument still remains true, that if I do the integration of d cos theta from minus 1 to 1, it is equivalent to integration of dy of y from minus 1 to 1, and therefore even this correction term will become 0. So alpha 200 is 0. So C n is equal to 1, and alpha, when alpha takes a value 200, is 0. That tells me that the first term which comes in this summation, or call it alpha over here, the first term which comes in this summation is 0. But still it does not tell me that all other terms are 0. What about C1 210, C1 211, C1 21 minus 1? And further I can go down this ladder and I will have more and more states. If any of them are non-zero, then I know that the wave function, ground state wave function, has been modified. So, so this is the computation for alpha is equal to 210. Here the Hamiltonian and this divided by the energy difference. Remember, in the downstairs, the energy difference is supposed to come ground state minus excited state. So 13.6 divided by 1 minus 13.6 divided by L square. So this will still remain true for n is equal to 1, L and alpha is equal to 210 or 2100 or 21 minus 1. All of them have the same energy and hence same energy difference compared to the ground state. So this term comes about. And there is a Hamiltonian's Z dependency, which is r cos theta and 210. Now, there is a typo I have not corrected. Here you will see that the 210, due to the fact that it has a 1 here. Remember, the states are marked by NLM. L is equal to 0 has no theta dependency, but L is equal to 1 has a theta dependency. L is equal to 1 will come with a cos theta. So the state coming over here has a cos theta dependency, and already there was a cos theta here as well. So the two terms combined give me cos square theta here and d cos theta integral I have to do. So it is no longer an integration of a kind dy of y from minus 1 to 1. This is dy of y square and this is not 0. So therefore, if I do this computation, C1210 turns out to be non-zero. So C1210 is not 0. So in this summation, at least one term is present which is non-zero. That means psi n1 is non-zero. Therefore, despite at the leading order, energy eigenvalue of the ground state did not change, the wave function changed. So wave function changed in a manner that it remained the same energy at the leading order. Again, I am saying it is only the answer at first order of lambda. In true picture, there is a net change or not would be known only from computing all order effects. All n is lambda is equal proportional to lambda, lambda square, lambda cube. All those coefficients need to be computed. But at least at the leading order, we have seen that the wave function changes, but the ground state energy does not. Okay. So this is the input story which we need to be aware of, that due to perturbation, the energy eigenvalue and the energy eigenstate both may or may not change. For energy eigenvalue, we have to compute one quantity which is En1 and check whether it is 0 or not. For energy eigenfunctions, we have to check all the coefficients C and alphas, not one coefficient, two coefficient, but all of them. If any of them is non-zero, that means wave function has changed, just like we saw the case for hydrogen atom ground state. Okay, so this is as far as the leading order effects of perturbations are considered. This is the first order correction coming from the change in the Hamiltonian from the exact solution which we could have obtained. Now we know that there are other sources of extra terms present in the Hamiltonian from various regions, be it the correct description of kinetic energy, correct description of potential, or some external applications. They all tend to put some extra Hamiltonians in the game. And we need to know, due to the presence of such extra terms, how exact is our knowledge of ground state, excited state, their energies, and so on. In some cases, it looks like they are very weakly perturbed, in the sense that ground state energy does not change much. For example, in hydrogen atom, for the ground state, we just saw that first order it does not change. Second order it might change, but it will be very small, as we will see later. But for some cases like the harmonic oscillator, we saw that even the ground state energy changed. So we need to compute these things every time and get to know what kind of changes this Hamiltonian brings at various orders. So let us stop this discussion on the leading order here. In the next discussion session, we will discuss about higher order effects, higher order corrections to energy eigenvalues. Okay, and in that process, we will see one interesting case where something of more interest comes about. If there are two different states with same energy, these are called degenerate eigenstates. So how to do perturbation theory for higher orders as well as degenerate energy eigenstates, we will deal with in the next discussion session. Okay, so let us stop here for today.